For the first time in 54 years, a human crew is preparing to observe the Moon from lunar orbit. Artemis 2 does not include a surface landing. It is a mandatory 10-day orbital flight designed strictly to validate the systems that will keep humans alive in deep space. NASA already proved the launch vehicle can fly with the uncrewed Artemis 1 mission. The challenge now is proving that the Orion spacecraft can bridge the gap between a kinetic test article and a habitable deep space laboratory. This introduces a very strict human-in-the-loop requirement. Autonomous robotic probes are highly efficient at gathering raw data, but they cannot evaluate the usability of manual flight controls, life support mechanics, or the psychological stress of the deep space environment. To understand how this flight works, we have to break down the launch vehicle architecture, the orbital mechanics of the trajectory, the hardware integration, and the biological experiments running on the crew themselves. Every system tested on this flight is a direct prerequisite for the Artemis 3 surface landing. Artemis 2 serves as an integrated risk reduction architecture for long-term deep space exploration. Building this architecture begins on the ground at the Kennedy Space Center, where Exploration Ground Systems manages the assembly of the launch stack. This structure is the Space Launch System. Powered by super-cold liquid hydrogen and oxygen, it provides the heavy lift capability to break free of Earth's gravity. While the rocket delivers the initial kinetic energy, the critical validation test takes place inside the payload spacecraft. The Orion spacecraft is split into two components. The lower service module provides power and propulsion, while the conical upper section is the crew module. The crucial delta between the first Artemis mission and this one is the activation of Orion's environmental control and life support systems. Engineers must prove these specific mechanisms can reliably regulate air, water, and internal temperatures under the dynamic stresses of active spaceflight. The integration of these life support systems enables the Orion capsule to function as a closed-loop habitat for the duration of the lunar transit. Executing this mission are 4 astronauts acting as human sensors: Commander Reed Wiseman, pilot Victor Glover, and mission specialists Christina Koch and Jeremy Hansen. After reaching orbit, the spacecraft performs a translunar injection burn, generating the specific velocity needed to leave Earth's gravity well. This initiates a 10-day transit, covering more than 685,000 miles. The crew will fly on a free return trajectory. This relies on orbital momentum, carrying the spacecraft on an uncoured path around the lunar far side. Moving at high velocity on a continuous loop creates a strict temporal constraint. The crew possesses only a several-hour window to conduct targeted lunar observations. During this brief window, the crew will execute manual flight maneuvers. Performing these operations in deep space, isolated from the communication relays of low Earth orbit, tests the vehicle's handling and the crew's reaction times. Orbital mechanics dictate the physical transit route, and they strictly govern the exact scientific window available to the crew. Back on Earth, the Artemis 2 lunar science team directs these targeted observations from the Science Mission Operations Room at the Johnson Space Center. This chart outlines the 10 approved science priorities. The absolute top priority is mapping color provinces and albedo variations across the lunar surface. The other Priority 1 objective is the real-time observation of lunar impact flashes while the crew watches. To capture this data, the crew logs primary audio descriptions through portable computing devices. For optical imaging, they rely on handheld Nikon D5 DSLR cameras equipped with 80 to 400 mm zoom lenses. They will also maintain an analog documentation process, using OneNote to replicate a field geologist's notebook. Because lighting and trajectory variables change dynamically, the exact list of flyby targets cannot be finalized until after launch. By combining manual photography, audio logs, and fluid target lists, the crew acts as a highly adaptable integrated sensor array. While the cameras look outward at lunar geology, the mission is simultaneously tracking the internal biology of the crew through the Archer program. Astronauts wear continuous monitoring devices that capture precise biometric parameters, including sleep cycles, physical movement, and stress markers. Archer assesses the psychological toll of deep space isolation, measuring how cognition and teamwork decay over the 10-day flight. Advanced biological tracking payloads monitor physical health. The Avatar project and immune biomarkers track how the human body reacts to the deep space environment. Alongside the biological data, Orion is carrying secondary hardware payloads, including auxiliary, shoebox-sized CubeSats. One of these is the KRAD cube. Mounted inside the Orion stage adapter, it deploys to measure deep space radiation exposure. These internal experiments force Orion to function simultaneously as a flight vehicle and a high-stress biological testbed. At the end of the 10-day timeline, the Orion module re-enters the atmosphere and descends for an oceanic recovery. Within 6 months of splashdown, NASA will release preliminary science reports detailing the immediate findings of the flight. All flyby telemetry and imagery will be permanently archived in the planetary data system, making the raw data accessible to the scientific community. The successful execution of manual flight maneuvers during the flyby directly proves the handling requirements necessary to pilot the Artemis-free surface lander. The biometric data gathered by the ARCHR program confirms whether the life support systems can sustain human health during long-duration surface habitation. Human lunar exploration has relied on the 1970s Apollo baseline for over half a century. Artemis 2 replaces those legacy systems with modern digital controls and high-capacity life support hardware. The ultimate trajectory of the Artemis campaign pushes past lunar orbit, setting the stage for a sustained human presence on Mars. The physiological and mechanical data gathered over these 10 days provides the exact mathematical foundation required to survive a multi-year transit to the red planet. The successful execution of this mission moves the Artemis campaign from theoretical design into a verified crewed operation.